Te voy a ver si te duermes.
Okay, so shall we? Okay, so let's start. Welcome everybody to our IFIMAC-ICMM seminar today. Today our seminar is in hybrid format, so we have people here in our auditorium, and also many people online. So thank you for coming. Today is a great pleasure to introduce our friend and colleague Leni Bascones. Leni, she works here at our institute, Instituto de Ciencias Materiales de Madrid, Material Science Institute of Madrid, from the CSIC, Spanish Research Council, and she's an expert. She's doing theory in condensed matter theory, and she's an expert in strongly correlated systems in general. And during the last few years, she has made many important contributions in the field of high DC superconductors, iron superconductors, focusing on aspects also related to Mott insulators and this kind of physics. And during the last 2 or 3 years, she's been working very actively in this new field of moire heterostructures, and in particular in aspects related to superconductivity there. And this is the topic of her talk today. So we are very happy to have Leni here. So please, you can start when you want.
So, well, first of all, thank you for the invitation to Ramon, to Sigmund, and to the rest of the organizers of the seminars. And thanks for the introduction to Ramon and to Sigmund for being there at the Zoom. It's a pleasure to start giving here in person and also at the same time virtual talks. So I think this is, except for teaching, I think this is my first talk in person in the last, I think, 1.5 years or more than 1.5 years. Okay, so let me start. So I'm going to talk about I'm going to discuss the correlations in moire heterostructures, and particularly I'm going to, as I will discuss, I'm going to focus on the ABC Trilayer graphene on boron nitride. So this is how this has gone. So this is a work that I have done in collaboration with Maria Jose Calderón from ICMM2 and with Alberto Camhaji from Universidad de Buenos Aires. So, well, I think that most of you have heard at some point to talk about the discovery of superconducting and insulating states in twist bilayer graphene, that it was done by the group of Pablo Jarillo Herrero almost 4 years ago. And so this field has started a new area, which is the study of the electronic correlations in moire heterostructures. So what they observe is they observe so a series of superconducting and insulating states which can be tuned with doping in this kind of system, which is 2 layers of graphene which are slightly rotated by 1 degree. So at the heart of this physics, of this complex phase diagram, so there is the fact that there are flat bands in this system, in which, so what this is essential because these flat bands are going to make that the kinetic and interaction energies are comparable. So this is what it will make that we can have correlated phases. So as I said, this has started a new field in which there are, so people is studying correlations in systems in which there is a moire pattern. So what you can see here is that, well, through the rotation of these 2 graphene layers, so you can see these new pattern in the crystalline structure in which there is a very big unit cell. Okay, so in which there are around 10,000 atoms per unit cell for this specific angle. So this kind of Moire pattern can be done whether through rotation angle, a twist angle between different layers, between two layers, or also aligning a graphene layer with another layer that has a similar lattice but a small lattice mismatch. Like, for example, if we have boron nitride with it, so we also have a similar Moire pattern, and so the lattice constant is also similar. It's of the order of 15 nanometers. Okay, so well, with this kind of process, so we can do many different kind of Moire heterostructures. So these can be based on graphene or in other different materials. So, for example, one can do twist bilayer transition metal dichalcoyanide. We can do like other kind of structures, like a bilayer. So two bilayers which are rotated through a twist angle or a twist trilayer graphene. But we can also say, as I also mentioned, we can also make devices in which what we have is some kind of graphene or a systematic or other material van der Waals heterostructure, like as there is here an ABC graphene trilayer that I will discuss later, which is aligned on boron nitride, and then we have a Moire through this kind of alignment. So in all these systems, people have observed different kind of correlated states, insulating states, metallic correlated states in many cases, and in some of these cases also superconduction states. There are many questions that are open at this point in this material. So the field it's extremely active and it's evolving very fast. So for example, it's still not clear whether superconductivity is electronic or phononic. From the point of view of the insulating states, there are many insulating states that are clearly it's clear that they come from correlations because they cannot be explained with single band physics. But what is less clear in many cases is, so in general, is the nature of these states. So particularly is how these states originate, whether Mott physics is playing any role, or whether what we have here are more conventional band instabilities, band-like instabilities. So it's all, so there are many issues open, like which is the role of Van-Hoff singularities, which are appear quite often in these systems, Fermi surface details, whether there is just stoner ferromagnetism. There are issues open regarding which are the symmetry breakings in these systems. So people have observed in some of these systems nematicity, ferromagnetism, thermodulation, but there are other states which has been proposed, and there is also an interesting interplay with topology. So at the heart of many of these discussions, what is essential is whether, so which is the nature of the correlations here. And particularly, so it's a question on whether these states or some of these physics, not necessarily all of them, some of this physics is related or to the one that has been observed in other strongly correlated electron systems, and in particular in systems like the high TC cuprates, the iron superconductors, or the heavy fermion compounds. So essentially in all these systems, there are all different families with different properties, but what is essential in this compound is that in the phenomenology there is strong influence of what is called the local correlation, correlations which are associated to electrons being, so they are fundamentally associated to electrons being, so to the correlations of electrons at the same site. So let me, so the paradigm is not the only effect, but the paradigm of these local correlations are the Mott insulators. So let me first of all start reminding what a Mott insulator is. Okay, so for that, let's first imagine that we have an atomic lattice with a single orbital per side and average occupancy 1. And so let's assume that we have kinetic energy and interactions, and that the interactions are just the interaction is restricted to the electrons which are in the same site. So this is the well-known Haber model, and so let's assume that the average occupancy is 1. So then, if we look at this system, so the kinetic energy, it's so average occupancy 1 means that we have 1 electron in each of these sides. So the kinetic energy in this is going to favor that electrons move from one side to the other, while the interaction energy, so it makes that if we have 2 electrons on the same side, it costs energy. So the system, if U is large, is going to try to avoid that there are 2 electrons on the same side. So if U is very large at some point for the system, it's going to be more interesting to localize the electron, not to allow them to move. So this means that if U is large, so we will have an insulator. This is a Mott insulator. Okay. So in particular, so this insulating state is driven by this repulsion, and you can realize that here I have not used to tell you that we need an insulating state. I have not used any symmetry breaking. So one of the main characteristic of this Mott state, in particular, this is what we call the Mott-Haber state, so is that symmetry breaking is not required for the insulator. That does not mean that we will not find, in most of the cases, some kind of symmetry breakings. It's just that it's not required. Okay. So if we are, as in this case that I have said, in a single orbital system, the system is going to be insulating only when we have this specific filling, like 1 electron per side, because if we have more than 1 electron per side, at some point for the system, it does not cost energy to move some of them, because we, as far as we don't change the number of double occupancies, but away from this filling, even if the system is metallic, there will be some features which are associated to the correlation. If what we have is a multi-orbital system, so we can have similar Mott insulating states at other integer fillings. So if we try to talk about, if we talk about Mott physics in this Moire heterostructure, we are not thinking on atomic lattice size, but we are thinking on this effective Moire size. So this localization is associated to this, to the Moire unit itself, not to the carbon atoms. So there are some experiments in some of the Moire heterostructures that have been observed experimentally, which are unconventional and that resemble the ones in systems like cuprates. But it's, as I will mention now, there are other features which somehow have suggested that Mott physics is not important. So the system that I'm going to study, that I'm going to discuss from now on, is the Trilayer ABC on aligned with boron nitride. So let me first introduce the system. So here we have a Trilayer ABC. I will now present you later just this Trilayer. So this is graphene, okay? So it's a trilayer of graphene. And so there are top and bottom gate. And so this allowed the system to, so we can tune with this, we can tune the band structure and the doping through these two gates. So now what is essential here is you can see here that there is boron nitride, okay? So normally there is both on top and below. And what is essential is that one of them is aligned with the trilayer because due to, as I have mentioned before, due to this lattice mismatch, so we can create one of this kind of moire pattern. Now, so here what you can see is that depending whether we put or this, we have this alignment or we don't have this alignment, what we are going to do with this is we can switch on and off the potential which is associated to this localization. To this, so this comparison are looking for similarities and differences in system with and without this alignment can be particularly enlightening. So in this system, this was just after twist bilayer graphene, the first system in which this type of correlated insulating states were observed. In fact, if some of you remember when Pablo Jarillo gave this talk at the March meeting, he already mentioned, okay, there has been, people has already observed similar insulating states in another system. So this was this ABC on boron nitride. So the question is whether there is any Mott physics in this system. So, okay, let me first discuss how is this system, and let me start by the ABC graphene trilayer. So we have 3 layers of graphene, and here ABC is related to how the two sublattices overlap on top of each other, 2 carbon sublattices. So already in the absence of the Moire system, so the close to the charge neutrality point, so close to the system that we have not doped, so the bands are already quite flat. So they are kind of cubic dependence. Okay, so you don't have them here cubic, you see some kind of crossings just because small trigonal warping really take out this cubic dependence, but you can see that they are really, in this region, they are really, really flat, okay? And now, so if there is a potential drop, so there is a perpendicular electric field that induces a potential drop between the layers, between the top and the bottom layer of the ABC graphene. So there is, so a gap is open in these bands. And so these bands become the conduction and the valence band become separated, and also they become even flatter. So you can see here in this figure. So now we align this trilayer with the boron nitride. So we have this moire. And so what we have done is we have enlarged this the unit cell, so it's much larger. So we have folded the band structure in a very small valence zone. And what you can see here is that our moire bands, so they have become separated from the higher energy bands. Okay, so we have these bands on this our mini valence zone, and here, well, in fact, we have 2 of these bands because we have in graphene we have the 2 valleys. So we have here 2 bands related by time reversal. So if now we apply this perpendicular electric field, so what we have is a valence band which is quite flat, and it has, due to this gap that is open here due to the electric field, so this gap, so this band, sorry, it's isolated from the other band. So we have a kind of single band, 1 in each valley, which is quite thin. So and then, so this band here, it can hold up to 4 electrons or 4 holes, let's say. So which is because we have this spin and valley degeneracy. And so these insulating states that I have mentioned before were observed when the system was doped with 1 or 2 holes per Moire site. And then the question is, okay, so which is the signature? So which is the nature of this state? So there has been very recent experiments without the Moire. So just the Trilayer, in which, so for a very small doping, just 1 hole per around 10,000 carbon atoms. So it's the doping similar to the one that is put in like 1 or 2 or 3 holes in this valence band, but just in the Trilayer. Okay, so what this has been observed in this experiment is that, so they have done compressibility measurements. I have not gone into detail, but what they have observed is that there are a series of ferromagnetic phases, so spin polarized or spin and valley polarized phases. So a series of ferromagnetic phases, even without the Moire. So just with an electric field, what is making, so here, in fact, what they have, we see here electron and this displacement field, so this electric field. So they see what you see here as blue regions are regions with negative compressibility, which is telling us that we have first order transitions. They have looked at this system, and there are a series of ferromagnetic phases, which, and even at some point, they later have seen even superconductivity in some regions. So the question is that in this system, so we don't have the Moire, and also the filling is per atom is very small. It's clear that whatever is observed in this system, there is no Mott physics at all. Okay, so these systems, of course, we also don't have insulating states. Okay, because so there is just a shift of some bands with respect to another. However, later, well, in fact, in the same work, they have observed that the compressibility that they measure, if they do the same kind of experiments with the Moire, have some similar features. And in fact, they also observe this kind of regions with negative compressibilities. So they are not exact, there are some similarities. And of course, here we have some features associated to the insulating state at the specific top. So in the Trilayer without the Moire, they said, okay, what we have here is just stoner ferromagnetism. So then their conclusion is that what we have in the Moire is the same thing, and that everything is just kind of stoner ferromagnetism. So the question is, to which point really has Mott physics been addressed here, whether we can say that here there is Mott or not Mott just with this. So what I'm going to do now is I'm going to discuss what is the kind of physics that Mott will give us in order to try to see whether we can look at the experiment trying to address this question. Okay, so now this is the system that we are studying. So we have this Moire, okay, so this Trilayer and boron nitride. So one interesting feature of this system is that depending on the sign of the electric field with respect to the boron nitride, this valence band we are interested in is trivial in the topological sense, or it's topological. So I'm going to focus on the case in which we have a trivial valence band, which makes that we can study the this band with a linear description. Okay, so I'm going to assume that this valence band is isolated from the rest, and that we can describe this system as a single band system. So the model, let's say the Moire linear function model. So here what we have is it's a kind of binary state for all the unit cell. Okay, it's not a binary for a single. So from the atomic point of view, so it's the sites here or the moire here are associated to the moirés. So what we have, so it was the Moire barrier function model was studied by Zhang and Sentil, and what they say is that, okay, so here what we have is a triangular moire lattice. We have, because we have these two bands associated to the valid degree of freedom, what we have is like two orbitals. So it's a kind of two orbital model in the Banner sense. And these two orbitals are related by time reversal symmetry. Okay. And so when we do the model, when one does the model, one gets Hopkins, which are complex up to the fourth neighbor. So these bands, as I have mentioned before, they depend on the Hopkins. So they depend on this electric field, this perpendicular electric field. And so I'm going to, in the discussion, I'm going to take this potential drop, which is 30 milli-electron volts. So then they also studied how are the interactions in this system. And so, well, the largest, we have different kind of interactions. We have density-density interactions. So interactions just charge between the electrons, which are in the largest is between the electrons, which are on the same side. This is the kind of Howard interaction, the on side, which is of the order for the, assuming this electric constant of A is of the order of 25 milli-electron volts. They also quantified interaction to first nearest neighbors. And there are also other smaller terms, which are exchange terms, Hund's coupling, and so on, or assisted hopping terms. What you can see here is that these exchange interactions, which are whether on site, this Hund's coupling, whether in between different sites, are much smaller than this density-density interaction. So what this suggests is that in a first step, one can just keep the density-density interactions, see what happened, and later one can consider the other terms. So what I'm going to do is, so we can see that the two terms are sizable. So I'm going to simplify even more the model. I'm going to, so to study the Mott physics and at the kind of feelings that I'm going to study, if this intersite correlation, if this intersite interaction, don't produce charge modulation, the main effect of the Mott transition of the intersite interaction is to somehow give a reduce. So it can be somehow absorbed into a reduced Howard interaction. So this is, of course, if we don't go to the limit of charge modulation. So I'm going, in fact, I'm going to focus on the case in which we have two holes in the system at the half-Helen. So, and I'm going to study the system, and what we are doing is we are doing dynamical mean field theory, studied with the continuum time quantum Monte Carlo approach of, well, as implemented in the Rutgers code. So what it means, what we can look with this dynamical mean field theory, it's able to address Mott physics, and it's doing it in a way in which, so for theories, the self-energy depends on frequency, but it does not depend on K. So in fact, essentially local interactions means this is this K independent part of the self-energy. Okay, so let me try to see what we expect. So this is our bands. Okay, so you don't see here the titles. So what I'm going to do first, I have said before that we don't need to have symmetry breaking in order to have the transition to have the Mott physics. So first, this is something that we can do in the technique. We are going to forbid to have a symmetry breaking. Okay, so I'm going to switch on U without allowing any spin or valley polarization or anything like that. And as I have said, I'm going to use U as an effective parameter. Okay, so this is at low temperature. So what I'm going to study. So let me first introduce U, which is not very large. Okay, so you can see the effect, and so you can see what is happening to this band. So there are two things which are happening. So our band is becoming, it's changing the shape, so it's becoming a bit renormalized. You can compare here in this plot. It's what is the dashed line is the non-interacting band, and then what we see in red is the spectral wave. Okay. So what you see is that this band becomes, it's starting changing a bit, but at the same time, it's becoming broadened. And at the same time, we are, so there is a reshuffling of the spectral wave. You can see how we are sending a spectral wave to higher energies. So if we increase more now the interaction, what you can see is that, well, this renormalization of the band becomes stronger, so it becomes more pronounced. This becomes a very, very thin band, but also you can see really that this becomes so kind of very weakly defined, and that really most of our spectral wave has gone to higher energies, okay? Until we increase it enough and we really have lost completely our band. So we don't have any more K-dependent band, okay? This, in fact, when we have really set all these spectral wave to these high energies and we don't have it here anymore, is when we have the Mott transition. So at this system, what we have, the Mott, so we have the Mott transition around 28 milli-electron volts, okay? So as many of you have imagined, this region where we have sent all these spectral wave are the Hubbard bands. Now, while it's not until 28 milli-electron volts, you can see that already at interactions which are like half of this value. So the band has changed considerably. And we have also sent already a lot of spectral wave away. So this is what we will see if we will be able to do angle resolved photoemission experiments, which in fact in these systems is not possible. So of course, this is leaving an imprint in the density of states. You can compare here is how is the density of states. This is a non-interacting one, the one that corresponds to this. So this is at the left, the one that corresponds to the non-interacting band. And so we can see this value is close, but this 24 milli-electron volts is close, but below the Mott transition. So you can see how this density of state has changed considerably. We have a narrow peak and close to the Fermi energy, and we have these Hubbard bands. So what I want that you see here is that, well, so here I've been discussing n equal 2, where we can have this Mott transition. So if we are at a value of n, which is not integer, we cannot have an insulating state, but you can see that we still have this effect on the Hubbard bands, and in fact, something that we expect to see is a doping-dependent density of state. So it's not. This is not going to be. This is not going to be just a shift of the chemical potential. With temperature, so the behavior of Mott system, it's also different to standard insulating states. So you can see here at the left, you have the spectral weight that I was showing for before for 23 milli-electron volts. And then, so here it's at low temperatures, and at the right is at a bit higher temperature, 6 milli-electron volts. And what you can see is that this was the part of the, so this was our still quasi-particle bond. So when the region where we still were having some well-defined bond, so still, but you can see that with increasing the temperature, so this coherent behavior has been lost. So somehow is that we have increased the temperature and the insulating state is promoted, in fact. So insulating behavior is promoted when we increase the temperature. Okay, so this is different, for example, with respect to the symmetry breaking insulating states. So another important thing that you can see here is that all this physics that I'm discussing is associated to changes in the spectral weight, which involve large energies. Okay, so you can see here that this changes in a very large range as compared to these energies that we are, so these temperatures that we are looking at. And so you see here this effect on the density of space, this large peak that we have at 120 milli K. So it's kind of melted when we increase the temperature. Okay. Okay, so let's now go to the antiferromagnetic, so to the order state. So, so the question is, what kind of order state do we find in this system? So in general, our models have the tendency to promote antiferromagnetism. So we are in a triangular lattice. It's not like, well, in a square lattice, it's clear that it has the tendency to give the nil state with spins or in this case, valleys. So like alternating. So in a triangular lattice, the lattice is frustrated, so it's less obvious. So there can be different order states. There could also be some other kind of spin liquids. Some of the states possible, maybe like 120 degrees or nematic states or different possibilities. So the question is, what is found? So there was a previous work by Chimiao-Si and co-workers in which they did rational Monte Carlo, and they studied as a function of Kunz coupling, and they observed a state which is, it's a kind of anisotropic antiferromagnetic ordering. In their case, so they can have antiferromagnetic spin ordering or antiferro valley ordering. So with Kunz coupling, they found that this antiferro spin ordering, it was promoted. Now, in their case, so the values that they show, so somehow all the gain in energy seem to come from Kunz coupling that we are not introducing in our calculation. So what we are obtaining is what we observe in our modeling, which the interactions are SU4 symmetric, the same for spin and valley. We observe an antiferromagnetic state. With the calculations that we have, we cannot say exactly which is the antiferromagnetic state that we have, but we believe that is this one. It's this state that breaks C3 symmetry. And so this order, we find it not just for this electric field, but also for other electric fields. But we don't find it if we just consider a simple triangular lattice with hopping to first nearest neighbor. So we believe that it's kind of stabilized by these long range hoppings in this system. So what we find is, what we can see is that we have some kind of local polarization at each side, and that in our case, it's independent whether it is spin or valley. So, and but what we see is that these states appear only at interactions which are kind of close to Mott. So we haven't found, in this system, we haven't found ferromagnetic states, for example, at the smaller interactions, but that could happen if the bond structure is a bit different. So, And then, so what is clear from this is that this antiferromagnetism is associated to the localization of the electrons. And this is also observed, this is our order parameter, which is the polarization. This is also observed if we look with as a function of filling, we find it only close to n equal 2, okay? And so, well, the energy that is involved in this antiferromagnetic state as compared to the non-magnetic state, it's of the order of 0.25 milli-electron volt, which compares well with the temperature that, or the ordering temperature that we find in our system. This state is slightly metallic. It's not insulating, but it's not necessarily Fermi liquid. It depends on the range of the parameter. And even if the energies that we find are small, so it involves spectral reorganization in the large energy window. So the question is, what means this? So what is this telling all this as compared to the experiments? So before, so the discussion was, okay, so in this Trilayer, when there was no moiré, one say, okay, so they are finding ferromagnetic states. And so they say, okay, this is just a shift of the bands. So if one increases in this system U, one can say, okay, so at some point you find a ferromagnetic transition. So what I have said is that in our case, at integer filling, if we increase U, so the band is, even without any kind of symmetry breaking, the band is strongly modified, even up to the point that it disappears. So if U is large enough, so this density of states that was driving ferromagnetism in the Trilayer will not be able, because it has just even disappeared. And in any case, we expect, even if we are at the smaller values of U, so one expects that these bands change. And so the question is, how small is this U in the real experiment? That is the issue. The other question is to say, okay, so is there any problem if, with a Mott perspective, so if one finds ferromagnetism instead of one finds antiferromagnetism, so is this telling us something with respect to the nature of these states? Well, so before I have told you that, okay, so these were the largest interaction. These exchange interactions look very small, and one thing, okay, maybe one can throw them away. But now you can see that the antiferromagnetic order that we have observed, it involves really an energy of the order of 0.25 milli-electron volts. So the question is that somehow this is comparable to the terms that we have thrown away. So in principle, of course, here one does not have the accuracy to say whether this exchange is 0.3, 0.4, or 0.1. Okay, so it's of the order of these energies, but somehow it really can be perfectly possible that in the experiment, this exchange between the electrons at different sites really win. So somehow finding ferromagnetism in this system is really not telling us whether about anything about really the nature of the system. I'm talking clearly about the moire and the insulating. So the moire close to the insulating state. So what is interesting here is that these energies are similar to other energies that can come from our system, like magnetic field, like a strain or something that maybe can help us to play with the system and tune to see whether we observe, and maybe tune different magnetic states. That's something that could be maybe done. There is now also the issue of Hund's coupling. So from the calculation, it's expected a very, very small Hund's coupling, but this is something that from the experimental result it's belief that there should be some Hund's coupling, not very clear exactly where it's coming from, but from other lattices, so from other degrees of freedom in the system. So okay, so let me just summarize. So we have seen that, okay, so if we are talking about Mott physics, we really expect kind of unconventional behavior. So we should not expect that well-defined bands, particularly when we are really at the insulating state. So, but we can really go beyond at temperatures above the ordering phase transitions, look at temperature dependencies, look at doping dependencies, because we should find anomalies. So this is kind of the way in which we should look at the nature or to verify or the opposite, to say that this is not happening. And also, well, we have found this antiferromagnetic state that breaks C3 symmetry, and that, well, so it's competing with the ferromagnetic exchange, but who knows if maybe at some point it can be cured. Okay, so thank you very much.
Okay, thank you very much, Leni, for this fantastic talk. So what we can do is, if you have questions here in the audience, and then we can move to the online audience. So questions here, anybody? Yeah, Luis, you can speak to the microphone.
Is this possible to include the very phase of the bands in this kind of calculation?
So the fact is that, so here you start with a kind of, we have started from a linear model. So in this case, we have a trivial band. So the question is that, so if for a topological band, I cannot do that. But sometimes there are some cases in which you can do some kind of effective models, including Moire bands. In this case, I think it's not possible, but we haven't really looked at that.
Okay, more questions? In the online audience, Sigmund? You know?
So far, no.
Okay, so maybe I have questions. So you were discussing as you increase the Hubbard, this emergence of this coherence peak in the spectral weight. So what is the actual role of this emergence of the coherence peak in the phases that you are studying? Because this is something that I missed.
Okay,
somehow.
so somehow is that.
Yeah, the strong renormalization of the bands is clear, but the coherence.
So the fact is that what this coherence, what is telling you is that you have a quasi-particle band.
Sure.
So this is what it's telling you.
Sure.
Now, the order phase that we observe, it's kind of associated to the local. So you can see that we only observe. So we only observe this order state when we are very close to Mott.
Yeah, you
and
see
somehow
the
this
physics,
is a kind of exchange, super exchange physics. So the ordering is more coming from these local electrons which are associated to the Hubbard bands. So we observe the ordering both in the metallic state when we have, in the metallic state but close to Mott, when we have this strong coherence peak, and in the insulating state, so where we don't have. So you see here, we observe here is Mott, the interaction for the Mott transition. And so here, so below this interaction, we have coherence peak. So the system is metallic. Above, we don't have this coherent peak. And we find in a range of parameters, both below and both above, we find this insulated state.
You have
so I have to say that I cannot say whether there is antiferromagnetism or not beyond interaction because there were kind of convergence problems for convergence. So I can't. But if the interaction is too small, we don't find it, and that can be studied. Yeah.
Okay. So no further questions, I guess. Sigmund, no further question online?
No question in the chat, no.
Okay, so then we thank Leni again for the seminar. Thank you.
Okay, thank you.